All right, so we're going to look at section 7.3, which is on solving trig equations for most of the class, and then towards the end we'll do a couple inequalities. But we're going to solve them graphically. What's nice about solving things graphically is you can solve pretty much anything. With algebra, which we are going to come back later sections, and we're going to solve equations using algebra, but we can only solve trig equations with algebra if they work out special. Okay, they either have to be factorable, or you can use quadratic formula, something like that. Okay, so something special has to happen. But graphically, we pretty much graph anything. So when you're solving a trig equation, how many solutions can you get? Yeah, you could get infinite solutions, or what's another case that could happen? Or no solution. That's all that can happen. You either have an infinite amount of solutions or you have no solution. So the idea is you first have to start by finding all the solutions within one period. Okay, and this is exactly what we've done algebraically. And once you find all the solutions within one period, you have to take into account the period of the function. Okay, so that means we have to remember how to find the period of all the basic trig functions. And in addition to that, eventually we're going to start looking at periods of higher powers. Okay, we're going to look at, like, what's the period of cosine squared or cosine cubed. Okay, so we'll start to look at higher powers. So any questions on that idea? Find all solutions in one period, and then take into account the period of your function to generalize all solutions. Okay, I think most of what I do today is going to be in radians, but everything we're doing in radians you could do in degrees. It just depends on what they're asking for. All right, so this is something algebraically we've solved, taking the inverse sine of both sides, but I want to practice solving it the way we're going to do graphically. Okay, and this is a pretty easy one to start with. So when we solve equations graphically, most of the time the goal is going to be to get it equal to 0. Can someone tell me in this equation what I would have to do to get it equal to 0? Yeah?
The inverse sign.
What's that?
Use the inverse sign.
So I'm not trying to get x by itself. If I was solving it algebraically, that's what I would do. Think of, like, if you had x equals 0.8 and you wanted to get 0 on one side. You just subtract that number so there's nothing left on the right. So subtract 0.8. And now you've got sine of x minus 0.8 equals 0. Now, this wouldn't be a good candidate to solve graphically because we have a way to do it algebraically, the way Kyle was already mentioning. I think it's going to take longer to graph it. But it's just a good one to show you the idea of how we're going to do graphing, because it's basic. Okay, so I'm going to type it in, sine of x. And it's very important you close the parenthesis, because it makes a big difference if that 0.8x is inside the argument or outside. But the first step was to find all solutions in one period. So what's the period of sine? 2 pi in radians. So now, when I set up my window, I need to set it up so that the difference between the min and the max is 2 pi, the x min and x max. What's one way I could do that? So I'm only looking at one period on the screen.
You want to make one negative pi and one positive pi?
You could. You could do negative pi to positive pi. Or you could do 0 to 2 pi. As long as you take x max and subtract x min, and you get 2 pi. Okay? In this case, I think what I'm going to do is just stick with positives, or non-negative answers. So from 0 to 2 pi. As far as how high and low we need to go, we don't need to go negative 10 to 10 on the y-axis because we're just dealing with sine. What's the highest and the lowest sine goes? 1 and negative 1, and then you're shifting it down 0.8. So it's like negative 1.8 to 0.2, yeah. So really, we need to go that high, and I need to change my mode back to radians. If you get something that ever looks like a straight line, it's probably because you were in the wrong mode. All right, so I'm looking at it, and it's a little tough to see, but I'm thinking it crosses the axis in 2 spots. And now I just need to calculate both those answers. Okay, I already know what quadrants the answers should be in because I'm looking where sine equals a positive number. Sine is positive in quadrants 1 and 2. So I'm expecting an answer between 0 and 1.57, and then an answer between 1.57 and 3.14. Okay, I'm going to calculate the first one. If somebody with their calculator can do the second one, that would be helpful. And make sure you calculate a 0. Okay, I accidentally pressed intersect. That will not help. Okay, so the first answer is about, let's say, 0.9, rounded off to 0.93. Okay, and did anybody get that second intersection point?
I got it, it was 2.21.
2.21. It's exactly what I expected my answers to be between. One's in quadrant 1, one's in quadrant 2. And it says to find all. So what do I have to add onto the end of each one of those answers? 2 pi n. And what does n represent? Any integer. So you can add or subtract any multiple of 6.28 to either one of those answers, and you can get the next 2 answers in the next period or in the period before. If n was negative, you'd be subtracting. Okay, so those are 2 answers. Now when you're doing this, especially when the trig functions get complicated, you can have a ton of answers. I think we're going to do one today that has up to 6, crosses the x-axis 6 times. For something like that, I wouldn't give you one on a test where it has that many, but maybe up to 3 or 4 times, but not 6. Because at that point, it's just getting tedious to keep calculating all the roots. It's just time consuming. All right, so basically what we're doing is we're finding the roots of the equation. This is something we've already said before. The only difference is we're doing it with trig. All right, so in the first part of the class, a few months ago, way back, we set an equation equal to 0. That meant you're finding the roots. Well, now we're just setting a trig equation equal to 0, and we're still finding roots. It's the same thing, just with trig equations. And I just want you to also remember this idea, that if you have a function, okay, that's periodic, and you set it equal to 0, well, now you're solving an equation that's periodic. Okay, so periodic, for us, basically means it has a trig function in it. Anything that repeats itself is periodic. All right, and this page, you don't need to write it if you already understand the concept, but it's basically what we've been doing. So the goal is, if you're finding roots, you have to start by finding all the solutions within one period. And then, after each solution, put plus the period times n. And remember, n is an integer. So that's just the format of our solutions. It's exactly what we did on example 1. Okay, but that's the key. All solutions within one period. The only thing you got to be careful about is, let's say this was your window on the calculator, and let's put my x-axis in right there. Let's say I graph this, and I asked you how many times that crosses the x-axis. Well, it's going to cross here and here, but what about this third one? what do you want to be careful about when you're writing all solutions within one period? That's a repeat. Okay? If this is 0 and this is pi, this is 2 pi. Well, 2 pi is a repeated answer. So generally, if you have an answer right on the left edge and right on the right edge of the screen, you only include one of them. So think of it, this is your interval on the screen. From 0 to 2 pi, not including 2 pi. So any questions why you can't include both edges of the screen? Because the right edge is a repeat of the left edge. So that might come up, or I think that will come up today. All right, so eventually what we're going to start doing is we're going to look at more complicated trig functions like that. Okay, what's happening here is we've got two trig terms, not to mention one of them is squared. We've never even seen trig terms squared. But does anyone have a guess at how you would find the period of a more complicated trig function? Something that has more than one term, or maybe even something you just have to start out by doing. Yeah?
I might have already answered that because I said I'm all equal to 0, but I'm certain on that.
Yep, so the first step will be to get it equal to 0, and we're going to have some problems that are not, like this one, example 3. So that will be the first step, but not in example 2, because that's already done. And the arrows are kind of a hint. To find the period of that entire equation, what do you think you have to start by doing? Yeah?
Finding the period of the individual pieces.
Yeah, find the period of the individual periodic terms. You don't have to find the period of the one. That's not a periodic term, just a number. But cosine squared and sine are both periodic. So we're going to start by finding the period of each term. And then the period of the entire thing is the LCM. Okay? It's the least common multiple of all the individual periods. Okay, so if you don't remember exactly what LCM is, think of this. Can somebody give me, what are the multiples of 2? Yeah, 2, 4, 6, 8, 10. And what are the multiples of 3? Yeah, keep going. So if I asked you what the LCM is, it's the smallest number in both lists. Well, we can do the same thing with pi's. Okay? We can do exactly the same thing. Let's say I put 3 pi and 4 pi. What are the multiples of 3 pi? 3 pi, 6 pi, 9 pi, 12 pi. And what about multiples of 4 pi? Yeah. So the least common multiple between 3 pi and 4 pi, it's like saying the least common multiple of 3 and 4. You just have to put a pi on the end. Okay? So let's start with sine, because I think we know the period of that, I hope. What's the period of sine? 2 pi. But let's look at cosine squared by itself. Okay? And if I forget to type in the rest of the function after, let me know. Because for now, I just want to look at cosine squared. But eventually, I want to type that whole thing in. Okay, so let's type in cosine squared. And you have to type it like this. Close the parenthesis, and then put the square. You can't put the square in the middle of it, but what's written on the board here and what I have here are the same thing. Right. And what I'm going to do is I'm going to graph this from 0 to 2 pi, so it's already set. And I'm going to see if I can look at the screen and tell how many times it repeats. Okay, how many times does it look like that graph is repeating? Twice. Okay, it starts at its highest, it goes down, hits 0, goes back up to its highest, goes down, hits 0, goes back up to the highest. So you're looking at 2 periods on that screen. And what's the width of my screen? 2 pi. So that tells you what the period is. The period is pi. Okay. Eventually, I'm going to give you some formulas in how you can figure out any trig function to any power without having to play around with it like that. All right, so now that we figured out the period of cosine squared, what's the least common multiple of pi and 2 pi? 2 pi. Now it's going to seem like that always comes up, and it does come up a lot. Okay, that period comes up all the time. All right, so now I'm going to graph the whole thing. So I've got 2 cosine squared x plus sine x. Is that a 1? Yep, plus 1. And my LCM is 2 pi. So set your window so that it has a width of 2 pi, however you want to do it. I'm generally going to stick with a positive part of the x-axis. Okay, so there's our graph. And it ends exactly where it started, which is perfect. So the next section on the screen would just be what I just traced, copy and pasted to it. Okay, so how many times does it look like it crosses the x-axis? Once, it could be twice. We might want to zoom in a little bit. Okay, it does almost look like it's twice, but if you keep zooming in, it almost looks misleading. Let's trace now. Because looking at that, I would say it looks like it does dip below it. It looks like 1 pixel row is lit up below the x-axis, but if we trace, okay, watch the y value. Okay, just to be clear, is that a negative number? No, that's just 0.000 and then a 5. Okay, so let's watch if we ever get a negative in front. Okay, so we just hit 0, and now we're still positive. So yeah, it actually never crosses the x-axis. It just touches it, and I was able to tell just by tracing. Usually you can't do that, but I can this time. The answer is 4.71. If I couldn't do that, what I would do is I would do second calc 0. And how often is that answer going to repeat?
Yeah, 2 pi.
Every 2 pi n. Good. Any questions on that one? Okay, the next one, Kyle already mentioned something we want to do to set it up more like this one. What do you think the first thing I'm going to do here is? Kyle?
Set it equal to 0.
We want to set it equal to 0. So, the way I'm doing it, I'm getting 0 on the right. So how would I move everything to the left? Yeah, so we got tangent x minus 3 cosine x. We don't have any numbers in front of x, which can affect the period. And we don't have any powers here. Well, other than what power is tangent and cosine both raised to? The first. So it's just the basic periods. What's the period of tangent? Pi and cosine. 2 pi. The LCM? 2 pi. So that tells me how I should set up my window. 0 to 2 pi on the what axis? X. Since I zoomed in, I messed that up, so I need to fix it. Now, cosine, what's the highest cosine goes? 1, and we're going to triple it, so it's going to go up to 3. And what's the lowest? Negative 1, and we'll triple it, so it's negative 3 to 3 for this part. But how about tangent? What's the highest and lowest that goes? It goes up and down forever. So when you have a graph that goes up and down forever, I mean, you can go as high and low as you want, but negative 8 to 8 is usually sufficient. Because remember, we're focusing on where it's crossing the axis. We don't care what's happening way up at infinity. So don't go too far with your y min and max. And I don't think I typed it in yet. So type in tangent x minus 3 cosine x. Okay, and how many times does it look like that one crosses the x-axis? Twice. Now, what I've done here is the way I picked my window, I broke this section and this section into two parts. This section that I'm tracing right here, and then that section, could be connected. If I slid my window to the left a little bit, you would see this piece right here. Does everybody see that? So you could choose a better window so you're not seeing this in 3 separate pieces, but only 2. But as far as finding answers, that doesn't matter. Just go second, calc, 0. I'll do the second one, if somebody else can get that first one. Okay, the second one is about 2.13. And how often is that answer going to repeat? It's going to repeat the LCM, which is 2 pi. Okay, and we're going to get another answer, which is not a repeat. Okay, you cannot get this answer from the first one. They're 2 distinct answers. Yep.
I got 1.01.
Right, 1.01, and that also repeats every 2 pi.
How come we only got one answer for the second problem?
Because it only crossed the x-axis one time. However many times it crosses the x-axis, that's your answers. Okay. Any questions on that? No? All right. Let's try this one. So let's start by finding the period of cosine x. Okay, what's the period of cosine? 2 pi. It's a vertical stretch by a factor of 2, but that doesn't really matter because it's vertical stretch does not affect the period. That's horizontal. Now, what's difficult about finding the period of this term? Two things make it difficult. Yeah? Yes, it has a horizontal stretch. That alters the period. So we got to take into account the 2. And there's something else that's changing the function. It has an exponent of 3. So cubing it also changes it. All right, so what we'll do is we'll graph sine cubed 2x. Don't let me forget to type in the rest of the problem after. But I just want to start by finding the period of sine cubed 2x. Okay? The 3 in front has no effect. So let's type in sine 2x, make sure you close it, and cube it. Okay, I've got a window from 0 to 2 pi. Okay, so I'll graph it and see if I can figure out what I'm looking at. And I really can probably tell by looking at it, but I can zoom in a little more, and you'll probably see even better detail. Okay, how many times is that repeating? Twice. It's repeating twice over an interval of 0 to 2 pi. So what's the period of sine cubed 2x? Pi. Anybody have a guess what it would be without the 2? Well, it's pi right now.
Oh, 2 pi.
It would be 2 pi. If you got rid of that 2, this 2 is a horizontal compression. If you take away the 2, it would stretch a little bit, and it would make the period a little bigger. All right, now let me type in the whole problem and see if we can figure out what's happening. So we've got 3 sine 2x. I don't think it's going to cube the 3. The exponent should just apply to the first term. So let's leave it, let's try it like that. Minus 2 cosine x. Okay, I know what the answers are supposed to be, so if it messes it up, then we'll know in the future. Always put parentheses around what you're cubing if you have a number in front. But I don't think you need it. Okay, LCM, oh, we didn't write the LCM. What's the LCM here?
2 pi.
Yeah, it's the same as what we've been doing. I already got it. And as far as the highest and lowest, well, -4 to 4 worked okay for the first term, but then you're subtracting 2 cosine x. So that might cause things to go a little higher and lower. So I'm going to try -6 to 6 and see if that fits on the screen. If it goes off the screen, it's not a huge deal, but I kind of want you to see the full picture. Okay. So how many times, try to make it a little bigger, how many times does that cross the axis?
6.
Yeah, 1, 2, 3, 4, 5, 6 times.
You have 6 answers.
Yep, so this one you'd have to calculate 6 roots. Okay, just to save us a little time, what I'm going to do is go like this, and I have all 6 somewhere. You get about 0.50, 1.25, 1.57, 1.89, 2.65, and 4.71. You wouldn't have this many due on a test because this problem really isn't, it's not, once you can calculate 2 or 3 roots, I mean, calculating 6 isn't testing anything new. You're just doing more of the same thing. Okay. And all of those answers would have a what? Plus 2 pi n. So a little sloppy with my notation, but that's basically plus 2 pi n to everything without writing it 6 times. Okay. Any questions on that one? Now, what if I wanted to see 3 periods on the screen? Not 1. What would I have to set my x max to?
6 pi.
Yeah, if you set it from 0 to 6 pi, you're going to see the graph we just did repeat 3 times. There's 1. There's 2. There's 3. Okay, you're seeing the same thing repeated 3 times. All right? So make sure when you're doing that, we're only focusing on 1 period, but they might ask you to look at more than 1 period in other kinds of problems in the future. Okay, but you don't have to worry too much about that right now. All right, so we don't have to keep kind of messing around. We looked at, I think, sine to an odd power. I think we did cosine squared, so we did cosine to an even. And I'm going to put a b in front of all of these. Because remember, the number in front of x, I think it was Matt that mentioned that that's a horizontal stretch. That also affects the period. So it's the power NB. Okay, so if you have tangent or cotangent, it doesn't matter if it's even or odd. Any tangent or cotangent function uses the formula pi over b. But if you have sine, cosine, secant, or cosecant to an even, that's the formula, pi over b. Now I put absolute value just in case b was negative. I don't think we have one where it is, but b, when you're finding the period, should be a positive number. So what's missing here? There's 4 cases here that are left out. The odds, right? Sine, cosine, secant, and cosecant to an odd power. All right? So if you have sine, cosine, secant, or cosecant to an odd power, and maybe you can come up with a shorter way to write this, I don't know. The formula is not pi over b. Anyone have a guess what it's going to be?
B over pi.
Still the same setup. B's still in the bottom. But it's 2 pi. Remember, sine to the first power, the period is 2 pi. Okay, so that's That's your two formulas, and now you don't have to play with it on the screen and try to figure out the period. If you forget these formulas, you can. But I think if you just remember them, it's easier. And again, these also could have a horizontal stretch in front of the x. So you have to take 2 pi and divide by whatever b is. So let's look at the previous one and see if that makes sense. Sine to an odd power. What formula should I be using? 2 pi over b. And what's b in this term? 2. The number in front of x is 2. 2 divided by 2, those cancel out, and I get pi. And that's exactly what we discovered by kind of experimenting and just looking at it on the screen. Okay, but if you don't want to have to do that, there's your formulas. All right, so the last thing we'll look at is solving some inequalities. Well, if you can solve an equation, you can solve an inequality. It's pretty much the same thing. The only difference is when you're solving an inequality, your answer usually isn't a single number. Does anybody remember what you get when you're solving an inequality for an answer? Like if I go back to this one, if I said, where is this function below 0? I would say from there to there, there to there, and there to there. Those three things that I just traced, what are they? They're not single numbers. Yeah?
They're a range of numbers.
They're a range, they're intervals. Okay? So when you're solving trig inequality, a lot of times your answers are going to be intervals. Very good. So start out just like you're solving as if it were an equation. But then you have to take into account the inequality. Is it asking you where something is less than 0 or where something is greater than 0? And you've got to keep in mind, is it less than or equal to or just a less than? That tells you whether or not you should include or not include an endpoint of an interval. Also, remember that on your screen, we are always going to include the endpoint on the left side. We are not going to include the endpoint on the right. And if you get any vertical asymptotes in a picture, that's going to take your interval and break it apart. Okay, you have to take into account vertical asymptotes. And for most problems, if you have a vertical asymptote, it's going to be easy to find. There's a few different things we can look at here. We'll look at a single inequality, a double inequality, and there's another problem that's kind of interesting to look at if we have some time at the end, but we'll see. Right, so let's solve that. And the first step here would be the first step as if you had an equal sign between those two. So what's my first step here? Yeah? Sure. I subtract cotangent of x. And now find the periods. There's no powers on any trig term. So what are all my powers here? My powers? Yeah, these are assigned to the first, cotangent to the first. And there's also no number in front of x. So what is b in this case? 1 and 1. So basically, it's just the basic function. What's the period of sine? And the period of cotangent? Pi. Remember, if you look back at your chart, it's cotangent to an odd power. Okay, period's pi. The LCM? 2 pi. So now I'm going to set up my window so that I go from 0 to 2 pi. I think -6 to 6 for the min and max is probably fine because it's going to go off the screen anyway. Bless you. Okay, so we get sine of x. And what about cotangent?
1 divided by tangent.
Right, and you got a reciprocal, that's how you have to type it in. And I like to put that in parentheses just so the calculator treats that as its own calculation. So I have sine minus cotangent, and I'm looking, bless you, I'm looking for where it's below the x-axis. So let's say graph. And I want you to look at this closely and tell me if these two curves are the same curve.
No.
No. I think you can really tell if you look right here, this one's a little sharper. This is much smoother of a curve. So these are not repeats. If they were repeats, then I would say we made a mistake with the LCM.
It kind of looks like that the two just like flip. Because the top of the first one has like that more of a sharper area.
Could be some kind of mirror image flip thing. We don't know. It could be. Yep. And now let's find our solutions. All right. So remember, my solution is going to be an interval from this section and that section. So I need the x values for the two intervals I just traced. Where does the first interval start? At what x value? That would be the range of it, but I'm taking the domain. Starts at 0. Now, my window here, does my window include 0?
No. Yes.
What did I say about the window?
Yes.
Yes, we are including the left endpoint. We're not including the right. But look at the function. What does it look like is happening at 0? And Sophie, what she said. So that means there's a what right at 0?
Vertical asymptote.
There's a vertical asymptote. So even though 0 is in the interval on the screen, I can't include it because there's an asymptote there. So that interval starts just after 0, and it goes right up to that first intersection point. Does anybody have that intersection point? Can you get it? Well, Kyle's getting that intersection point. Can I include it? Kevin, sorry. Wait, who's getting it? Someone's, I don't know.
I was kidding.
Oh, I thought actually you were getting it. Oh, I thought Kyle was getting it. Can I include that or not include it?
Which one?
This point?
You can.
No.
No. I have to be strictly less than 0. I can't equal it. So that means the symbol right here will be
Parentheses.
parenthesis. And now, Kevin, do you have that point?
0.90.
0.90. Okay. Now, let's just look at the other interval. Can I include that point?
No.
No. And it's starting somewhere, it almost looks like it's right in the middle of the screen, but what does it look like is happening again in the middle of the screen?
Vertical asymptote.
Another vertical asymptote. Because it's right in the middle of the screen, where do you think it would be?
3 pi.
Let's check. If it's at pi, let me actually type in pi. Let's trace, and I'll type second pi, and there is no y value. It's an error. Okay, so there is a vertical asymptote at 0, and that's where the second interval starts, right after the vertical asymptote, and it ends right there. Okay, where does it end?
5.38.
Did you get that just by looking at it with your eye,
Yeah.
without using a calculator?
Yeah. I use a ruler.
That's pretty good. Any questions on that? Now, keep in mind that this isn't the only section you're going to see this. You're going to see this again repeated how many units later?
2 pi.
Yeah, so on each interval, that's to the whole interval, and that's to the whole interval. Okay? So you're going to get this again 2 pi units to the right, and again, 2 pi units to the left.
Not like the-
Okay. Any questions on that? So it's the same idea. You still got to calculate the roots. It's just now you got to be careful with bracket or parenthesis. This one I want to graph as is. I'm not going to get it equal, or I'm not going to get 0 on one side. Anybody see what's different about this problem? Look at what's on the left versus what's on the right.
A regular inequality or a trigonometry inequality?
One side has trig and the other side is just algebra.
Yeah. So what did we say earlier, that when you have a trig function, and I mentioned this word, it falls into what category of equation? And it has to do with what gives us infinite answers. It's periodic. So that's a periodic term. It repeats itself. Is x squared minus 1 periodic? No, it draws it one time and it's done. So that means when we solve this, are we going to be adding a plus 2 pi on my interval? No, there's only going to be one spot where this is true. You're not going to see the parabola repeated again later on. So let's graph it, and let's look at what it looks like. I need to probably adjust my window. Yeah. Let's do zoom 7. So that's a trig zoom. I'm just looking at a bunch of periods of sine. And there's the one time the parabola is drawn. You're not going to see the parabola repeated again right here. If it was, then you'd get more solutions. But it's only one time. So where's the solution here? Where are we looking? Think about what it's saying. This greater than or equal to that. Yeah?
Right inside the parabola.
Yes, inside the parabola. So from here to here. Let's just call that x1 and let's call that x2. You'd have to do second calc, intersect, and find them. But just to save time, let's call it x1 and x2. And that's where the periodic function is above the parabola. Can I include x1? Yep, it can equal each other. And can I include x2? So what kind of symbols would I put?
Brackets.
Bracket, bracket, x1, x2. Okay, the point here is it is not periodic, so it doesn't repeat later on. Okay, any questions on that? Yeah.
So how would we answer that question? Would we present you with x1, x2?
Yeah, you have to find x1 and x2.
Oh, okay, that's nice.
Yeah. Yeah, you just have to find them. Okay, any other questions on that? All right, let's take a look at this one. It says 0 equals sine 1 over x. Let's type that in and see what it looks like. Okay, and I'm going to do zoom 7. All right, so how many times does that cross the x-axis?
Oh, I don't know.
About 5.
Looks like a bird getting caught.
Yeah, 4 times.
About 4 times? All right. Why don't we, let's zoom in a little bit. Instead of going -8 to 8, let's go like, does everyone agree that all the answers look like they're between at least -2 and 2?
Yeah.
All right, so let's zoom in there. Let's take a look at it.
Oh.
Any thoughts now? 6?
25.
Let's try negative,
It's getting large.
let's try negative 0.5 to 0.5. I think that still will contain all the solutions.
I'm scared.
Actually, I don't know.
Any stuff?
12? What is that? 2, 3, 4, 5, 6, 7. that last time. But
Infinite.
Yeah, there are infinitely many solutions. So it's a pretty simple graph, and it's not like it's got a lot of stuff. But sine 1 over x has infinitely many solutions. Okay. Anybody know why?
Because it just wants to be free.
Not a wicked.
Well, let's think of this question. Okay? This right here is an angle. It has to be. You can only take the sine, the cosine, or the tangent of an angle. So what angles can you take the sine of and get 0 as an answer?
Oh, yeah.
isn't there like four?
It's a lot, but you can generalize them. Can anyone give me, like, what's an angle what angle you could take the sine of and the answer comes out to 0? No, sine of 90 is 1.
0.
0,
360.
which is a repeat of 0. So 0, 2 pi,
Pi.
pi. What would be the next one after 2 pi?
3 pi over 2.
Nope, 3 pi over 2 is 270. That's the sine of negative 1.
4 pi.
4 pi is another one, but 3 pi. Okay, so basically, how could you summarize that?
Every 180 degrees.
Yeah, anytime you take an angle that's a multiple of pi, you will get, if you take the sine of it, the answer comes out to 0. All right, so basically, as long as 1 over x is equal to some multiple of pi. Okay, does everyone see that? 1 over x has to come out to either pi, 2 pi, 3 pi, 4 pi, any multiple of pi. Well, let's solve that. And to get x by itself, just flip what's on each side. What do you get if you flip what's on the left? What do you get if you flip what's on the right? 1 over pi n. There are all your solutions. And n can be what? Any integer. So let's look at our table. Let's let n be 1. Yeah, we could do 4. What's pi times 1? Pi. So let's try 1 divided by pi. 1 divided by pi. There's a solution. That's where it crosses the x-axis. What would be the next integer after 1? 2. Let's try 1 divided by 2 pi. 1 divided by, yeah, I think I need parentheses around it. 2 pi. There's another time it crosses the x-axis. Okay. 1 divided by, what would the next one be?
But Mr.
What? Oh yeah, it's the calculator can't, it's not smart enough. What about the next one? Where would the next one be? 1 divided by 3 pi. That's another time it crosses the x-axis. 1 divided by 4 pi. 1 divided by 5 pi. So what's happening to these answers? They're getting closer and closer. 1 divided by 100 pi is another answer. 1 divided by 600 pi. 1 divided by 1,000 pi. 1 divided by any multiple of pi is an answer.
So why don't they all just come up with 0?
Well, because the calculator, it can't really figure out the algebra we just did, so it's using a method to try to approximate the answer, and it got 0.0000000000002. So the calculator can't do algebra, but it's trying to figure it out using what it knows. Okay? So the point is, you can keep zooming in, but you're going to get infinite answers. All right. And the last one we'll look at.
Oh man, there's more.
Oh yeah. Is a double inequality. So with a double inequality, the only thing you have to do is graph the first part in y1, the second part in y2, and the third part in y3. And you just have to look where your graph of y2 is pinned between y1 and y3. So it's like it's sandwiched between two other things. Okay. What does the graph of negative x look like? Just y equals negative x. It's a line with a slope of and a y-intercept of. Yeah, so it's a line with a slope -1, goes right to the origin. How about y equals x? Yeah, it's a line with a slope of 1, and it goes through the origin. So let me graph those two first. All right, so let me graph negative x in blue, and I'm going to graph positive x in black. And let's do zoom 7. Okay, so there's our graph in blue. There's our graph in black. You know what? I want to zoom out a little bit. So I'm just going to press zoom 3 just to get a bigger picture. And now the last thing I'm going to type in is x sine x. Well, when you put a number in front of a function, what does that do to it? What kind of stretch? Vertical. And what kind of thing is this?
Variable.
It's a variable. So this is a vertical stretch that is variable. It's a constantly changing vertical stretch. So let's see what it looks like. So it's a sine function, but the height of it gets higher as you get further away. So now the question is, where is the graph in red where is it above the blue and below the black? Yeah, everything from 0 on. It's above the blue, but it's below the black. Everything from 0 on. Okay, so that's a double inequality. Okay, and now the last thing we're going to take a look at
No,
is the homework. Okay, so the homework probably going to be due on Friday. Okay, it's page 401. It's all graphing. You need a graphing calculator for pretty much every problem. So it's 5 through 7, 11 to 15, 19 to 25, just odds, 29 through 31, and 33 to 37, just the odds.
So do we have to draw the graph? We don't
No.
have to draw the graph, right?
You just do it on the calculator, and that's it. And as a reminder, there will not be a test this week if we have no school tomorrow. If we do have school tomorrow, then there will be a test on Friday.